All right, I'll get started in just a minute. And in the meantime, if I just want to call your attention to the URL on the screen in case you're one of those people who likes to look at your screen more than look at the projector. Okay, is it okay to start? Great. Thank you for attending. My name is John Regehr. I'm a professor of computer science at the University of Utah. I'm going to talk about undefined behavior today. And I just want to add that I would certainly love to get questions while I'm talking. I'd rather kind of be interactive and address the kind of things that you'd like to hear about rather than get through all my slides. Okay? So what I'm going to do today is talk about what undefined behavior is, why it exists, what are the consequences, and sort of what can we do about it. And if you noticed from your program, I have this slot and another slot from 315 to 415. And so these topics will be spread across the two slots, just kind of however it comes out, depending on how interactive you are and how fast I talk. I'll try not to talk super fast, although I sort of by default do that. So let's talk about interface design. Interface design is hard, right? Interface design is never easy, and designing failure modes of interfaces is one of the hardest parts. As you can see here on the screen, I've showed just sort of a really easy question, or a question that should be really easy, which is what should our language implementation do for the square root of -1? And you can see that there are some, a number of choices, and none of them is obviously the right answer, independently of everything else that's going on. All of these things could be the right answer. And the different choices have a lot of effect on our programming system, whether we return an in-band error or an out-of-band error, whether we have a language with exceptions, whether we have complex numbers. These are pretty big decisions, and getting these right is hard. It's sort of these global design decisions that make designing programming languages and programming systems, really this really challenging thing that it is. So you can see that on the bottom, one of the possible choices for this is undefined behavior. And so undefined behavior is just a design choice. So it's just a design choice. It's one of the things we can do when a program does something, but it's this pretty extreme design choice, right? And the reason that it's extreme is that out of all the choices we can make of what the compiler is required to do, or what the programming language implementation is required to do, when the program does something, this is the one that imposes the fewest requirements. And you can see that I've regurgitated a little bit of language from the standard here. So undefined behavior is pretty commonly seen on hardware platforms. And what it does there is gives the hardware manufacturers a way to say, here's a register. We're going to put something in this register later, add some functionality later. We haven't done it yet. And really, really, really don't mess with this register, because then later your software will be broken once we do something there. So that's sort of the most basic and most defensible use of undefined behavior, is to warn you away from doing something where nobody wants to do error checking, and where nobody wants you to rely on any particular thing happening when you do that. So this is kind of the sort of baseline usage of undefined behavior. And it's kind of crept into, it's sort of pushed into other usages as well. So what I want to do next is make an analogy. And it's a pretty loose analogy, but I'll just ask you to bear with me for a little bit. So here's my loose analogy. So this is a derivation that many of us ran into in grade school. And the derivation starts off with something sensible, and through a series of steps, mostly good steps, ends up with an indefensible result, right? So you can see that we've ended up proving that 2 equals 1, and each of these steps, at least to somebody maybe in grade school or possibly high school, looks okay. And so which is the wrong one? Yeah, we had an obligation before performing this step of the derivation to prove that we weren't dividing by 0, And once we do that, things go wrong, and we end up with a completely nonsensical result from a series of what seem to be pretty normal steps. And the reason I use this example is because I think it really kind of helps convey the flavor of what's going on in undefined behavior, where nobody tells you what's going wrong. You sort of have to observe this for yourself by knowing all these rules. And it doesn't just kind of necessarily give you sort of a predictably bad result. It kind of makes the whole thing garbage. And you can see this entire thing, our proof here is garbage, right? It just doesn't make any sense because we've admitted an inadmissible proof step. So anyway, it's just an analogy. I don't know if you like it or not, but I think I sometimes use this, and I think it's helpful in it's helpful in understanding undefined behavior. And let me do another example. So here is a little program, and what this program tries to do is something which is undefined by the standard, but which a lot of people say, or have said in the past, is okay, which is an underlined memory access. And the reason you would say this is okay is because you just know that your compiler is targeting an architecture that supports supports memory references to any byte address. And so since you know this, this should be okay. And this is the kind of argument that people sort of put forward for doing undefined things. And it's a very similar argument to one you kind of hear pretty often, which is, I know that we have a 2's complement platform. So of course, overflowing an integer should have 2's complement behavior. And people it's really hard to kind of escape from the mindset where you make these assumptions about the platform and you lose track of the fact that C and C++ define these abstract machines that really you have to think of them as not really being tied to the platform. And so the analogy I'm going to use here is one that I didn't come up with. It's one from one that somebody posted on the internet a long time ago, which is that saying that this program should work because x86 supports unaligned memory references. I'll just let you read it. It's a reasonable analogy here, and it's wrong. And so of course it all sort of hinges on what do we mean by playing basketball, right? Or do we mean holding a ball and moving, or do we mean something more sophisticated, like adhere to a collection of rules that we all understand as being basketball? So is that sort of clear? And anyway, it's a terrible argument even so because, x86 64 has move DQA anyway, which has the A is for aligned, right? So it has so the program I just showed you doesn't crash on x86, but programs not too much more complicated, compiled by GCC, will crash on x86 because you get the compiler to emit a move DQA, and then the program actually does crash, right? So it's not even true. The basic reasoning isn't even true here. But even if x86 didn't have that instruction, or if the compiler never generated it, it still wouldn't be true because the compiler would be allowed to assume that things were aligned and do something wrong with your program, do something better that you didn't intend with your program. Okay. So C and C++ have lots of undefined behavior. They have undefined behavior to avoid overhead in the generated code. They have undefined behavior to avoid compiler complexity. The compiler gets to assume things that would either be difficult or impossible to prove from first principles if the compiler weren't allowed to just assume them. And then they have undefined behavior to provide compatibility across different implementations of the language. And if you look at the history of undefined behavior, the way I understand it, and this could be wrong, I haven't talked to the people responsible, but the way I understand it is up through K and RC, the use of undefined kind of seems to mean you get an unpredictable result if you do something. As in, it's this kind of bounded thing, which means that if you shift a 32-bit integer by 44 bits, you might get something weird in that particular value, but there's nothing that really implies that it's going to sort of tank your entire computation. So that then it's only in ANSI where they put in the language which said the compiler is allowed to assume, or the compiler makes no guarantee about what happens when you execute undefined behavior. But so that seems to be when some kind of a line was crossed. And we went from undefined behavior as being this kind of limited thing to undefined behavior as being this very powerful tool for the compiler to assume that something doesn't happen, and thereby to end up not making guarantees about programs that do the things that are undefined. So let's look at this question. So this question is kind of fun, is does undefined behavior avoid overhead? And of course, the answer is absolutely yes in many cases, but you have to look at this on a case-by-case basis. And so let's look at a really simple example. So the question is something like the shift operation in C++ made more efficient by the fact that shift is undefined when the shift exponent is too large? So what we have to do is we can observe that the standard should say something about what happens when you shift the 32-bit value by 44-bit places. It should say something, right? It shouldn't just be silent on this issue. So since it has to say something, what should it say? Well, hardware platforms do at least 3 different things in this case. And there's probably more. So the standard has to say something, but it can say anything it wants. But it wants to be efficient. So of course what it says is this is undefined. The compiler just assumes that this overlarge shift doesn't happen. But what if we wanted to standardize on a particular behavior? So if the behavior that we choose is masking off the shift exponent by the number of bits, by the width of the shifted value, So of course there's trade-offs here, right? That may not be the behavior that we want for an overlong shift, but if it is the one that we choose, and this is one that, for example, WebAssembly has used, then basically this mandates a mask instruction, an AND instruction in front of every shift. And with that extra instruction, we would get this kind of uniform behavior across all implementations. And so now we can move on to the question, is adding an AND instruction in front of every shift a reasonable thing to expect a compiler to do? And some compilers, like WebAssembly, say, sure, fine, we'll just take the pain of these masking instructions. And C and C++ have sort of said, no, that's not right. And so in this case, we can see exactly what the cost is. We add an extra instruction any place we can't prove that the shift exponent is in bounds. And so is that a good trade-off? This is open to debate. It's not a super easy question. But in this particular example, the actual overhead is very clear. It's an AND instruction. Does that kind of make sense? No questions yet? I'm talking so fast that everybody's quiet? Good. Okay, so yes, this undefined behavior avoids overhead, and that's what it avoids. So let's talk about undefined behavior a little more globally. So Appendix J of the C standard, and here I'm going to kind of, unfortunately, kind of switch around between C and C++ some, and for most purposes, the two languages aren't functionally different for purposes of undefined behavior. All right, they share the optimization parts of the compiler largely, right? And so then that's where most of the undefined behavior magic happens. So I'm going to kind of switch between talking about the languages. I'm sort of sorry to do that at CppCon, but I'll have to do that. So there's a list in the back of the C standard which lists kind of most of the undefined behaviors. It's definitely not complete, but it gets most of them, and it has almost 200 undefined behaviors. And as far as I know, this doesn't exist for C++, so nobody's sort of made this list, and this would be very nice if this list existed. It's tricky because some undefined behaviors are undefined only by sort of implicitly undefined. Does this kind of make sense? You'll see sort of wiggly language in the standard, like the implementation is allowed to assume that. So if the implementation is allowed to assume X, what that really means is not X is undefined behavior. Does that kind of make sense? So there's some places where things are undefined only by implication, but it really would be nice if this list existed, and if this list were being expanded for every new version of the standard. And I have on the slide here an example of a undefined behavior that just seemed to have appeared if something went from unspecified to undefined just in C++ 17. So having a complete list would be good. I'm not sure that it's a really big deal because the sort of heavy hitters in undefined behavior we know, and they're well known. But it would be nice to have a complete list. And I always feel kind of a little slighted that the C++ standard doesn't have this Appendix J, which is, I think, kind of a very nice part of the C standard. So let's talk about, yeah.
I just had a comment about that. You haven't even touched about what the standard library considers undefined behavior. And basically, they do that by defining requirements, conditions that must be satisfied before you make the call. And if you don't satisfy that, you make the call, you forget it's undefined behavior. And there are lots more of those.
Yeah, so Marshall's observing that if we look at the standard library in C++, there are even more undefined behaviors, and that's absolutely the case.
The canonical example of that is sort. You pass a comparison function that doesn't actually impose a straight reordering. It's like, yeah, we're not safe.
Sure. So let's look at what happens. What are the things that happen when your program executes undefined behavior? Well, one thing that can happen, and this is very nice, is your program breaks immediately. It's seg faults or whatever. Another thing that can happen is the program keeps going as if nothing happened, and either maybe it kind of keeps going in a good way, maybe it kind of keeps going in a bad way, and something goes wrong eventually. Another case is the code works as you kind of hoped it would have worked, but you have a problem moving forward. So for this particular compilation of this program, there was no problem, but changing the compiler options, changing the compiler version, changing the compiler supplier, one of these things might make the undefined behavior behave badly at a later time. And I like to call these time bombs. They're problems in the code that are latent. They're waiting to go off at some point in the future. And of course, not all undefined behaviors execute at all normally, right? Some undefined behaviors only execute when somebody owns your code. And so out of these four, I really would just want to kind of talk about the two middle ones, because case one is sort of easy and uninteresting, right? We just debug it. And case sort of unnamed case 4 here where we don't know how to trigger it, this is Kostya's deal, right? This is why we need fuzzers and stuff, right? That's not my job here to talk about that. So it's really these two cases where undefined behavior does something weird or where it might do something weird. That's kind of the focus of the talk today. Oh, that's okay. So the question is a math exception undefined behavior? The answer is no. The answer is that the division by 0 is undefined behavior. The math exception is what might, that's the symptom that you might get on some platforms. But the standard doesn't say anything about integer divide by 0 producing an exception. That's pure x86.
As in it's undefined behavior. What's defined on it.
It's the abstract machine which makes it undefined. But this is the thing is, if the abstract machine guaranteed that you would get the exception, then that would be one thing, but it doesn't guarantee this at all. I mean, that code could be elided or something if the compiler decided to do so. If a compiler could prove that that a division by 0 happened, it wouldn't need to trigger the exception. And I strongly bet that you can construct cases where it does that. So let's look at what's been happening over the last 25 years or so. So one thing that's been pretty awesome to watch and to see happening is that the undefined behavior detection tools have been getting good. So starting maybe, I don't know what the first undefined behavior detection tool was, but something like Purify maybe in the early 90s would be a good example. So this is one of the first, or maybe the first memory overflow detection tool. And those of us who were around in the 90s remember that was awesome. When you got Purify, I mean, everybody, I don't know how many of you remember first running Purify on something, and even stuff like LS would have all sorts of problems in it. I mean, it was incredible. So Purify was this thing which rewrote your binary to insert checks. Maybe not unlike Valgrind, except that it was not a just-in-time compiler as much as a sort of a load time compiler. Anyway, so these tools have been getting awesome, and they're just in the last 5 years there have been enormous improvements. But on the other hand, compilers have been getting cleverer and cleverer at exploiting undefined behavior to improve code detection. And even sort of simple things like improving the inliner can greatly increase the scope of the undefined behavior exploitation that happens on your program because it exposes more code to the compiler's analyses, or it puts code together where the compiler analyses can look at it all at the same time. So compilers are getting clever, and this has been causing, since maybe around 2000, these kind of time bombs to go off. And one of the interesting ones that's been kind of fun to watch is integer overflows. Those sort of, a lot of 90s era C code assumed that integer overflows were 2's complement. And since like 2000, GCC especially has been making those sort of one after another kind of not be 2's complement behavior. And this has caused little sort of, so it's not been a huge issue, but it's been sort of a niggling source of correctness bugs for a number of applications for a long time.
Yeah, about the integer overflow, one thing I try once in a while is to run a piece of program that's one shift like a while. And just try to run the two trunk compilers, run GCC, and it just compile dash dash that. What do you think about that?
So the question is, what should one shifted left by 31 do? And isn't this one of those cases where the different standards have different things shifting into the sign bit? This is one of the ones where you have to read the fine print for real about what version of the language you're using, because the standards committee has in C99, I believe that's undefined to shift a 1 into the sign bit always, and that was perceived as, I believe, breaking too much software, and they've backed off on that. So that was a really nice example of the committees taking feedback and backing off on something, which probably provided pretty dubious optimization value in the first place. Okay, so besides these two things, of course, security has become this paramount concern in developing software. So the consequences of undefined behavior in the real world have gone up dramatically since 2000 or so. So this is just a tiny rhetorical question. What happens when you go to a compiler developer and you tell them that your program, which executes unaligned memory access, is broke because you changed the optimization level or upgraded the compiler? Well, the compiler developer informs you that there are these things you shouldn't do, and please just don't do them because it's not their problem, right? So one of my kind of more fun, this is sort of small of me perhaps, but one of my more fun moments was when we started running the tool which became part of UBSAN, so detecting integer overflows. This is like what happened when you ran GCC. Is it just kind of like, so GCC, the GCC developers are a little bit famous for sort of telling people just stop with the undefined behavior. You know, it's not our problem, it's your problem. But of course, GCC was full of undefined behavior. It was full of these integer undefined behaviors. And so it's a little unfair to pick on GCC, right? Because basically all old programs, you know, this sort of 90s era C and C++ code contained a lot of undefined behavior. And it's just sort of how things worked at the time. And pulling that code forward has been one of our major ongoing problems because it requires a bunch of maintenance and fixing because things that used to work break. Or maybe even they never worked, but the security problems have become so much more severe. So what are we going to do about that? What are we going to do about all this 90s era code? Well, one thing we can do is go back and fix all of it. That would be awesome. Another thing we could do is just stop dialing up the optimizer. That would maybe not be awesome, but that's a possibility. And of course, we're not going to do those things, right? We're mostly going to kind of do a mix of these things. But we're stuck with a lot of code that doesn't want to get fixed, at least aggressively. And we're definitely not sort of dialing back the optimizers in any systematic sense. So now I want to sort of take a look at some specific examples for undefined behavior. And this is going to be kind of a mix of C and C++. And I'm going to just admit up front that I cherry pick my compiler versions somewhat when I make these examples. So if you type in the code here and run it with the compiler I said, it might not give the result that I said because I might be using, you know, GCC 5.4 instead of 5, and you have 5.5 or 6.5 or whatever. Okay, so I just have to sort of, you know, say that up front. But this particular one that I'm showing on this slide is generally pretty robust across versions of GCC and Clang for a long time. So what this program shows is a function which compares, the function foo, which asks whether x plus 1 is greater than x. And so mathematically, of course, that's true, right? X plus 1 needs to be greater than x. 2's complement-wise, that's not necessarily true because x might be int max. But C-wise and C++-wise, it is true again, right? Because either the result is undefined, in which case it doesn't matter, the result is irrelevant, or it's true. Does that sort of make sense? So the compiler can do this little case analysis, and that case analysis will let us infer that the function is always true. But the fun thing about the program here is in the same compiler, at the same optimization level, in the same program execution, the compiler asks the same question twice, says different things. So you know, the thing being illustrated here is that there's no requirement for consistency. There's no, you know, this isn't like implementation defined behavior, right? This is something where the compiler says right after it, one another that x plus 1 is greater than x and is not greater than x when x is int max. So of course it's an undefined program, right? It's an erroneous program. It shouldn't have done this. Upsan would have detected this. But if we do this, the compiler is free to sort of mess with us a little bit. So that's kind of a fakey example, right? It's not necessarily very interesting realistically. So here's one that may be more interesting realistically. So here's a integer overflow caused by shift by too far that was in an old version. This is maybe 10 years ago or something of Google Native Client. And so what happened is they had a mask operation shown in the little code fragment at the top towards the top of the slide. And that was masking off some low bits of a number. And they refactored the code in some sort of a routine refactoring that none of the code reviewers noticed to be the second snippet of code on the slide. And the problem is that the shift exponent, the nap align boundary, ended up being 32. And shifting 1 left by 32 places, you know, if one's a 32-bit integer, then this is undefined. And what the compiler did is basically drop this mask from Google Native Client silently, causing the sandbox to be weaker than it should have been. And so if you think about it, this is like kind of a little bit of a worst case scenario, right? We have something which is a sandbox. It's designed to be enforcing security properties on this containerized code, and it's not, but it sure looks like it is. And if we don't have a test case for this specific case, then we're sort of hosed. All right, so this showed up on the Google Native Client mailing list as sort of a scary example of the kind of thing that can happen if you aren't explicitly checking for undefined behavior in a code. So like I say, that code just went away. And there's lots of other examples of code going away silently, and some of the more famous examples, and I'm not going to go through them in detail, but you might have seen these where people use uninitialized data as entropy in random number generators sometimes. This is sort of poor always, right? This is never like good at all. But the compiler can make it so much worse by sort of transitively seeing that none of the code that depends on that matters really. because it's undefined code, and the compiler can go sort of clean up with a fairly broad scope if it wants to. The compiler can clean up that kind of code and just delete it. And again, we have this, the flavor of the thing happening is that the source code looks one way, the object code looks a different way, and if somebody really doesn't go dig in, we're never going to see it. All right? This might be my single favorite undefined behavior example. So P is a malloc cell. And let's just assume, for purposes here, that none of the mallocs fail, right? So like, we don't need to check return values to make this defined, right? So the undefinedness here doesn't have anything to do with malloc returning null. So P is a malloc cell. Q is a realloc of that malloc cell. So as soon as Q takes on a valid value, P has disappeared, right? P is a dangling pointer. Now P, of course, still has some sort of a value in its bits, right? But we're not allowed to indirect through it, even though it's probably going to point to the same place that Q now points to. Does that make sense? I mean, we didn't change the size with the realloc, right? So realloc would be stupid to actually do anything here. But in any case, logically speaking, in terms of the abstract machine, P now became dangling. So as soon as we store through P in the third line of main there, as soon as we store through P, the program makes no sense, right? Now it's gone undefined. Anyway, so let's keep going. So we store through P, we store through Q, and now we ask if P is equal to Q, then print something. And so the compiler goes ahead and it decides that P is equal to Q, and then it prints two different things for P and Q. Like what? So this is one of those things where you say to yourself, well, what is the compiler thinking? But it's really an error to talk like that, right? Because the compiler isn't thinking, right? It's just this collection of rewrites and this collection of replacements that just sort of glom your program into some sort of binary that emits, right? It's not thinking anything, and so that's the best way to think about these kind of programs.
Did you take a look at the disassembly of this code?
The question is, did I look into disassembly of this code? And no, and I doubt it's interesting, right? Because the program probably almost completely went away.
And so not that I've looked either, but I expect what's happening here is P and Q don't alias because their lifetimes don't overlap. And star P gets 1, and then you get 1 back out. Star Q gets 2, and you get 2 back out. So those get constant propagated. But the P equals Q doesn't get constant propagated.
Actually fires at runtime, probably. That's right. That's most likely what happened. Yeah. So does this program make sense to everybody? Did I sort of explain it adequately? So let's look at another one, and this one, this is another one that I like. So we have some code now. So if we define a debug flag, a debug macro, we're going to print the string pointed to by P. And then if P is true, we'll call a bar on P. And so now let's compile that without the debug flag. So we'll compile that without the debug flag. So when you look at the assembly code that gets generated, it looks pretty good, right? The assembly code says that we're going to test the value and conditionally call the bar function. So there's no problem, right? Okay, so now let's define the debug flag. So we'll define the debug flag, and now the printf gets optimized to put s, so don't get distracted by that. That doesn't mean anything. But what happens is that notice that we now didn't conditionally call bar. We unconditionally called bar. So why did we do that? Somebody tell me quickly. Yeah. If we had dereferenced, if P had been null, then the printf would have been undefined, right? Since the printf, so there's two cases. If P is null, the printf is undefined, the program is logically irrelevant. So the compiler has no obligation. So the compiler is allowed to assume that P isn't null since there is a printf. So why emit the test, right? So I've constructed the example fairly deliberately to show that, the sucky effect. It's almost like sucky quantum mechanics or something, right? We didn't want looking at P. We didn't want printing it to affect the semantics of the rest of the program, but it did. So this is yeah.
Yeah, I've actually seen stuff very much like this in my code, except it wasn't debug, it was log. Somebody
Sure.
had gone through later, added a bunch of log. And when you turned on log, the program misleading.
Yeah, so the comment is that logging can have the same effect. And yeah, this stuff can certainly happen for real. That's right.
I've taken advantage of this with break statements. Like if you put a printf in there, it forces the compiler to
Actually generate the code, the switch. So here's another function. So this one calls memcopy, and then if the source pointer was null, aborts. And so it should be no surprise, right, that the jump to memcopy occurs, right? Because if it was null, that memcopy would have crashed anyway, right? So at first glance, this looks just like the previous example, right? But it's not. It's not just like the previous example because n could have been 0. So the way this works is, even if n is 0, even if we're not copying any bytes, the standard says that you have to have valid pointers p and q for memcopy regardless of the value of n. So the inference is, the compiler is allowed to assume that it's a null pointer. And what this particular thing does, this is actually a little bit harmful in practice. This particular one burns people because you'll have a loop that's doing memcopies in it. And sometimes it's easier to have a memcopy with 0 at the last iteration of the loop, a memcopy of 0 bytes. Instead of jumping out of the loop somehow, you go ahead and execute the code. And so this is all fine, right? It's a little bit cleaner loop structure because the memcopy is just not going to fire. But you can get into trouble because the compiler can then assume that the arguments weren't null, even though they could have been at that point in the code. And this can lead to unexpected consequences. Does that sort of make sense? So the compiler is getting a data flow fact that many people wouldn't have expected it to get. And like I say, the standard is clear that you're not allowed to call memcopy with invalid pointers even with a 0 argument. So we're all to blame if we write the code. But on the other hand, this is one that's tripped up people for real. Oh, lib standard C++ bug because of this? Okay.
And they did something like this and then tried to delete the pointer. But their delete operator had a test for not null, which had a line.
Exactly the kind of thing, sure. So let's look at another one. So here we have a program, or it's not a program, a function which assigns 5 to the pointer through the pointer h, and then assigns 6 through the pointer k. And you can see in the assembly code that there's a very easy, nice correspondence between the assembly code and the C code. The store through h turns into the first move. The store through k turns into the second move. And then why didn't we just return 5? Why do we actually have a load following the 2 stores? The pointers might have been aliased. The pointers might alias each other. They might point to the same integer, in which case we can't just return 5, right? We need to return 6 when the pointers alias and 5 when the pointers don't alias. And the compiler knows this. The compiler is very smart about this kind of thing, right? So it's all, compilers generally do very well with this kind of constraint, even though as people reading assembly code, often it's like we look at the code and we're like, why is it so sucky? And it's because the compiler is doing the right thing, most often, and seeing that there's aliasing relationships, even when we as humans knew that there weren't. So if we adapt the code just a little bit by making k a pointer to a long, so now h is a pointer to an int still, k is a pointer to a long. So you can see that the move of 6 became a move q. So you can see that this is now a 64-bit move. But also the function just goes ahead and returns a constant 5. So the aliasing couldn't happen here when it could in the previous code. And this is because of the part of the C and C++ standards that we often call the strict aliasing rules, where pointers to different types are assumed by the compiler not to alias. And this gives us, as programmers, an extremely powerful tool for telling the compiler that things don't alias each other. And there's a lot of code, iterating over vectors and things. There's a lot of code where things like iterators would just be loading and storing from RAM constantly if the compiler didn't do type-based alias analysis. And the type-based alias analysis, the strict aliasing-based optimizations allow quite a lot better code to come out in some cases without sort of heroic compiler optimization. Okay, so that's all good. But it's sort of nasty, though, that even on a 32-bit machine, so I didn't show you 32-bit code here, but even on a 32-bit machine, the same exact thing happens, right? So even when size of in and size of a long are the same, the rule still applies. So now the compiler is kind of being a little bit, right? It's being a little bit nitpicky with us. But the optimization is not valid if h is a pointer to int and k were a pointer to unsigned int. Does that kind of make sense? So the compiler has these extremely specific rules about when different pointers to different types could alias each other. And these are fairly hard to get right. And this strict aliasing stuff has been if you really look at code, some large fraction of code is broken with respect to the strict aliasing stuff. Because, if you think about it, well-typed high-level code just isn't going to have the kind of pointer casting that's required to break the strict aliasing rules. But on the other hand, why are we using C and C++, right? It's most code, most real programs somewhere at some point get some typecasts in them and end up falling afoul often of the strict aliasing rules. It's quite hard to avoid breaking these rules. And consequently, it's not that uncommon, and I'll talk about this more later, it's not that uncommon to see real programs that compile with the strict aliasing stuff turned off. Because we just don't know where stuff is broken often. So here's one where I had to go back to a bit of an old version of Clang to get the compiler to generate the code that I wanted. I don't know if this was fixed. I don't know if the thing that I'll talk about here was fixed on purpose or accidentally, but the recent versions of both GCC and Clang have been doing something friendlier than what the code is showing here. So what the code does is function foo calls bar and then does some math. And if you look at the assembly language, the issue is that the integer divide instruction, the IDIV there, 4 instructions down in foo, precedes the call to bar. Does that make sense? So there's no reason at first glance why the compiler should care, right? It can reorder instructions fairly freely. But the issue is that, what's the thing about the IDIV that's kind of funny? Yeah, that's a trapping instruction. If we divide by 0 on x86, that's going to throw a trap and terminate our program. And so that generates something which is so it's undefined behavior. So the compiler doesn't care, but it's something that we can see happen. And this externally visible behavior that happens because of the IDIV isn't considered external behavior, right? It's undefined behavior, and the compiler's obligations have sort of ceased, if that makes sense. So if we take this program and we generate kind of the obvious wrapper for it, we're going to call foo with 0, and we're going to provide an implementation of bar that prints something. This is what happens, right? You call Clang without optimizations, and you run the program, and it prints hello and then terminates from a divide by 0. You do it again with the optimizer turned on, and it doesn't print hello because the instruction which terminates the program preceded the divide. So this is sort of this is something that I personally kind of hate, right? Because the whole reason I put that printf in there presumably it was like a got here, right? I got here, and so we didn't crash. So now I sort of have I've bisected my program into the part which could have generated the crash and the part that couldn't generate the crash. And now that bisection has potentially been invalidated by some instruction reordering. Well, okay, so the comment was undefined behavior can travel back in time. So yeah, exactly, right? So undefined behavior can travel back in time. And so this is yeah, go ahead.
So the reason that you can no longer do that, we stop doing that, is because bar could call exit and then won't reach undefined behavior.
I was thinking for an exception.
Or throw exception, or some other.
So you're saying that was stopped on purpose because we didn't know that bar was a pure function.
That is an invalid transformation.
Yeah, okay. Okay, good. Well, that's good to know that was stopped on purpose. Okay, good. Sure. Yeah.
Probably with printf we still could do that as long as it knows that it doesn't throw or it returns, then it's probably valid.
The question is if the compiler had seen the printf, if it might have been able to see that didn't throw or didn't call exit. Yeah. Good. Anyway, so the kind of cute thing about this one is that the time travel aspect of undefined behavior is actually explicitly spelled out in the C++ standard. So this is I've just grabbed from C++ 17 here, but it says that the order the undefined behavior sort of precedes the instruction or the statement that caused it. And so this is so it's sort of explicitly allowed. Okay. Still happy? Still with me? All right, now I'm going to show you one where this is the most artificial code fragment ever. It's explicitly designed to show you something. It's not real code and it's not good code. So what it is code that returns 1 if Fermat's last theorem has a counterexample within A, B, and C less than 1,000. All right, and otherwise doesn't return. And I've explicitly made it so that it doesn't return. I've explicitly structured this in an extremely specific way to prove a point. But the point is, this, looking at the code, it shouldn't return 1. It shouldn't return true unless Fermat's last theorem can be disproved within this bounded bounded space of the space of integers. Is that do we buy that?
The integers can't overflow.
The integers can't overflow here. That's good. So the question is, yeah. So if we could have integer overflow in the multiplications, then my whole program would be bogus, and the compiler could break it a different way. But the bound of 1,000 is chosen to put us just below 2 billion, right? Yeah. Yeah. So we're going to barely stay within 32 bits here. That's right. So there's no integer overflow. So we take this sort of silly code that's doing some format stuff, and we wrap it in some C++ code which just calls format, and then and the most Clang 5 will just happily print that Fermat's last theorem was disproved. And of course it didn't. Of course right. Obviously the theorem isn't false, and obviously the compiler didn't find values for A, B, and C that disproved it. Right. What it did was terminated an infinite loop because that loop didn't contain any side-affecting instructions, and this is explicitly allowed in the standard. And I was kind of complaining about this a number of years ago, and Hans Bem wrote a nice note about this issue, which explains exactly why this is a good design choice and why it's hard to do something different. It's actually pretty awesome. I really recommend reading it. Hans is this extremely smart guy and persuasive author. And so I was all mad about this issue, and then Hans wrote this, so I was like, all right, well, whatever, he's right, fine, whatever. But the funny thing is, though, is that this particular issue irritated enough embedded systems developers that in C11 they put a loophole, which is that if you have while constant expression, that's an infinite loop. All right. So while one or something equivalent is an infinite loop for real and can't be terminated by the compiler, but other even syntactic forms, right? This is nothing about the semantics of the code. Other syntactic forms are still vulnerable to this particular thing in C. And like I say, what I believe happened is that enough people got irritated with the while one loops in embedded software where you're trying to hang the processor at the end of some loop and just take interrupts. Enough of those were terminated and the processor dropped into garbage that people put some pressure on the standards committee to add this loophole. Like I say, I didn't hear that. I didn't hear that story, but that's what I believe happened. Okay, so what does this do? This sort of forces us to put some sort of a side effect in a potentially infinite loop, or else the compiler can just sort of drop us out. And so if I had gone back to the code and put in, a malloc or touch a volatile or anything like that. Sorry, say again. Yeah, returning A would. Yeah, trying to print the actual counterexample would have generally caused the compiler to not do the thing that it did. That's right. That's right. Okay, so here's the deal. So as a developer, you have to obey all of these rules, and you have to obey them all the time. You have to obey them consistently. You have to obey them all the time. And by default, nobody tells you when you break a rule. And this recipe has led us to sort of serious problems, starting with maybe the Morris internet worm, right? So something 20-some years ago, what was that, 88? So starting with the Morris internet worm or something like that, when buffer overflows in Finger Daemon and things were turned into a nasty virus. We've been sort of getting burned by this stuff for a long time, and it's not a very it hasn't been a very good situation. So it's getting better now, but it's sort of getting better, sort of slowly and in pieces. But anyway, I just wanted to kind of paint the picture of the situation as I see it. All right. Okay, so let me switch gears some. So what I would like to do now is talk about what we can do about it. And this is not going to surprise anyone, right? The things we can do about it. None of these things should surprise any of you. So let's talk about it, though. So one thing that I feel very strongly about is that code reviewers need to be thinking about undefined behavior. So the code reviewers need to understand undefined behavior, and they need to be sort of on top of this issue. And so it's pretty reasonable as a code reviewer to ask the person who wrote the patch, what's the proof, and you don't want a mathematical proof, but what's the informal reasoning why this particular line can't invoke undefined behavior? And I think it's absolutely reasonable to do that. And if people put up a fuss about asking, you ask them to proof, just say that I told you to tell them to do that. So let's just sort of look at an example. So the function foo here just executes a shift. And so what's the precondition of function foo? What has to be true before function foo executes, or else our program is undefined? And so, well, all of us know the first one, probably, which is that the shift exponent has to be larger than or equal to 0, and also less than the width of the shifted value. So we all know that one. But on the other hand, there's another one which is much more often violated in real code, which is that the y high bits of x have to be clear. And whether it's y bits or y minus 1 bits, I mean, there's a little bit of ambiguity there based on the version of the standard, but there have to be some high bits clear. And so, like I say, this is, I'm very serious that when somebody has this code, if there's any doubt as to whether those preconditions are true, you should, as a code reviewer, you should put up a fuss and say, what have you done to prove that those things are true? And they should put in an assertion if they can't prove it, or there should be something. Because this has to be true. And it doesn't make sense to ask somebody to test the case where it isn't true, right? It just can't ever be false, or else the program's broken. So let's talk about, yeah.
Does this mean a barrel shift is a valid implementation of left shift?
No, so the question is, does this mean a barrel shift is a valid implementation of left shift? I'm not sure what to do with that.
A rotate.
Oh, the question is a rotate a valid implementation of left shift?
Because if the bits have to be clear.
Yeah, I suppose it is. That would be a fun code gen change to put into a compiler and see what happens. Yeah. Yeah. So reasoning about preconditions is hard, right? I mean, this is program verification stuff, and people, and pushing these things around the program to the place where they all need to be, and especially pushing preconditions past loops. This is really hard stuff, and we want to offload this to tools. But on the other hand, this is stuff that, as a computer science teacher, this is stuff that I really try to beat into the heads of the people that I teach. Is that really people need to be capable of this kind of thinking. And so, like I say, I think it's absolutely reasonable when reviewing patches to sort of to make people produce these little proofs, if it's if it's an important part of the code. So that's kind of manual static analysis by static analysis in your head. But also there's we of course have static analysis tools, and I don't need to say too much about these. What I want to talk about first, really briefly, though, is unsound static analysis tools. These are the ones that are designed to miss bugs. And so designing tools that miss bugs by design is awesome, because these can provide, in many cases, a much better value proposition than tools which are designed to not miss bugs. And so here, of course, I'm talking about things like compiler warnings, tools like Covariety and Clockwork, Clang Static Analyzer, and all of these things that are allowed to miss bugs are super awesome, right? They're going to look for stuff that's definitely wrong with your code, but they're not going to find everything that's wrong with your code, because that's just generally way too hard. So sound static analysis is a whole different can of worms, and this is something where so a sound static analysis tool is one which is not allowed to miss bugs. And so a tool that's not allowed to miss bugs, if it says that there's no buffer overflows in your program, then it's essentially, that's equivalent to the statement that I've proved your program is free of buffer overflows. And these kind of tools, I've spent a lot of time with them, and they are sort of hell on earth to use. They're just horrible, horrible tools to use. The state of the art for C++ is much worse than it is for C, and that's on the C++ committee, basically. I mean, that's on C++ design. C++ is just really, I mean, I've talked to people while they were working on C++ static analysis tools, and it's really hard to do. It's not easy at all for C, right? I mean, static analysis is fundamentally a hard thing, but the C++ as it currently exists has really made things hard for these people. But so there are some tools that can do sound reasoning about C++. Not very many, and they require a lot of hand-holding, basically. You sort of have to become an expert in the tool. It's not like an unsound tool where you kind of use it and get value from it. And if it doesn't provide value, you kind of don't worry about it. These tools you have to invest, and you have to, you really, really, really sort of need an expert. And to some extent, the companies selling these sound tools have had sort of a bad luck selling the tool and better luck selling the services of people who know how to run the tool. Does that kind of make sense? Because the tools are that hard to use that, that they really require somebody who knows how to baby them along. And so my personal belief is that more of this kind of sound static analysis will happen in the future. But the gap between where we are now and applying sound static analysis to Chrome or something is really a vast gulf that may never be bridged. So I'll tell you what. I'm going to stop here, and I'm happy to take questions and stuff. And I will switch to the next. So I'll start talking about dynamic tools in the next part of the talk. Okay. I feel like I've been talking long enough, and my throat's all dry. Thank you.